Okay, so I'll continue our discussion today of the Kondo model. Let me just remind you. So what we have is a bunch of itinerant electrons, sometimes called the conduction electrons, that are hopping on some lattice, which is generally in high dimensions. I'm only showing one dimension. And then there's one single impurity atom, which has an extra orbital on it, sometimes called the d orbital, because it's typically the d orbital of a impurity atom like manganese and copper, and that's sitting on this side. And then we consider the limit where there's strong interactions on this side. So the net result under appropriate conditions, if you have strong interactions, then this side basically has a spin, which we spin a half, which we label by the vector SD. And then the Kondo model, the Hamiltonian, is the conduction electrons with some dispersion. And then an interaction with the Kondo exchange coupling JK between SD, the spin on the impurity, dotted. Let me write it here as spin of the conduction electron. And the spin on the conduction electron is related to the C operator by the usual relationship for the spin density. It's C dagger 0 of sigma Pauli matrix alpha beta C0 beta. So this C0 is basically, this is the side C0. On this side, you create an electron with the side C0. And you have a coupling between them. And this coupling can be obtained in exactly the same way obtained this super exchange coupling in the Hubbard model. The notes had a slightly wrong expression during when I presented it last time, which I've corrected now on the notes that are online. And the derivation is identical to the Hubbard model, so there's really no subtleties there. And basically, what you then find, roughly speaking, out of the magnitude of this there's this hopping matrix element here as W between the impurity side and the conduction electron. Then just like in the Hubbard model, the Kondo exchange coupling is W squared, where it's T squared over the repulsion of the electrons on this side, which is called UD. It's not exactly equal to that, it's of order that. So there's a prefactor, which is a bit more complicated, which is not exactly the same as in the Hubbard model, because in the Hubbard model, you have exchange between two sides, say this side and that side. There's a U on both sides. Here, there's only a U on one side. So that changes the energy denominators a little bit, and you get a slightly different answer, but that's about it. Okay, so this is the model that we want to study. And what makes it hard and also makes it interesting is that this spin operator here is a highly constrained operator. It's it's a qubit. It just has two states on each side, but just describing that qubit is very complicated. And the reason it's complicated is that you don't have a Wick's theorem. They're not free particles. They're highly constrained to be just the particle can't just hop off this side, but it can only flip its spin. So nevertheless, you can do some perturbation theory in JK by the usual time-ordered perturbation expansion, except you don't have the luxury of Wick's theorem available to you. So this has actually been done in the book, and this time I actually copied the chapter from the book. So there's a whole section here where they treat the Kondo model in time-ordered perturbation theory. So they have free electrons coupled to the conduction electron, to the impurity spin SD. Then you look at the conduction electron Green's function, and you expand it out, and in the usual way, you can write it as a time-ordered product of the free electrons operators times the time-ordered product of the spins. So this you evaluate using Wick's theorem, And this you evaluate literally by hand, just by commuting the spins by hand and seeing what you get. And you get various Pauli matrices whose traces you have to evaluate. So when the dust settles, I mean, here's the pictures drawn here. We've got various spins, and you take some expectation values, and then you've got Wick's theorem being applied to the conduction electrons. So there's at order J cubed, which is how far you have to go. It's a bit of a messy calculation, but all the details are here. And when the dust settles, you get an answer, which I will just quote and then try to interpret. So this is the answer that you get, that we end up needing, which is over here, which I put in my notes in our notation, just quoted it. So the answer that we have is here. Okay, so what's happening here, if I can just show a picture of it. So roughly speaking, you have the Green's function, G for the conduction electrons, and it has just the conduction electron going merrily on its own, but then the conduction electron can come in, it can do all kinds of things, interact with the impurity, and that's represented by this T matrix, T of I omega, and then it goes out. So this has some momentum K here, this will have momentum K, and there's no memory of the momentum K. In fact, nothing depends on the momenta except the external legs. So the task, really, the whole entire Kondo problem, on which 15 years or 20 years was spent of the community to understand it, is just understanding the frequency and temperature dependence of this T matrix. Okay. So there's an expression here that obtained, I just told you, and here it is. Okay, so that's kind of where we were. A quick summary and any questions? Okay, so if you look at this T matrix and you just evaluate it at order J cubed, you certainly get a divergence. And it's a divergence at 0 frequency and 0 temperature. So as frequency and temperature go to 0, usually those are very nice limits for a Fermi liquid. If you're computing the compressibility or the specific heat or anything, you can take the temperature goes to 0 and there's some fine, nice, well-defined answer. But in this case, you get a divergence. It's only logarithmic, and it seems similar to the BCS type log. And of course, that's something we're going to explore a bit more today. And so we want to, first of all, interpret this logarithm and figure out what the consequences are. And the consequences here are quite interesting, and they led to the development of the RG, the renormalization group. And let me just give a summary of the basic RG argument, but I'm not going to go into it in any detail because we're going to get the same answer by a more general method, a method that generalizes to other physical systems very shortly. So anyway, if you look at this particular answer for the T of omega, before we do this involves basically summing over all the conduction electron states. There's a sum over Q, and there's a sum over K. So the log term comes from this, and let's just imagine that EQ, which is outside, is just 0, and there's a J squared here. So just summarizing and paraphrasing, then the T of omega that we have, I won't get all the factors right here, is something like J squared, JK squared. And if you look at the limit of that other expression is 1 plus some constant times sum on K over JK over mod EK. If you just figure out what it does at small temperature, this is kind of what it looks like. Okay, when you put all the, and now you can very easily see where the divergence is. because you know that anytime you have a sum over k of any function of ek, in particular mod ek, that's equal to the integral over the density of states, d of e over mod e. And as usual, we can approximate the density of states, but the density of states at the Fermi level, which I call, no, sorry, d of 0. In approximate integral 1 over mod e. Okay, and this integral has an upper bound because there's some finite bandwidth, and I'm going to call that bandwidth d, or the total band is 2d. It goes from minus d to d. That's the width of the band, whatever it is. Okay, so this has then an integral. This has a divergence as e goes to 0. And that's the log that we worried about. Of course, that log is controlled at finite temperature, finite frequency, which is what the expression that I showed you. Okay, so this is the kind of thing that you get. And the idea of the RG, this is not a Konus RG, but I'll just give you a lightning introduction. When you see these kind of very singular effects in perturbation theory, what you realize, what you have to do to control it and understand its consequences, and is to take this term into account in some self-consistent way, not just first order in perturbation theory, but do it over and over again. And the way you include it over and over again is you just, instead of doing the full integration, so you have an expression here, jk squared times 1 plus jk d of 0, and then you have this integral of dE. And what you're going to say is that the basic trick is, instead of doing the full integral, I'm just going to do the integral over a very tiny window near the high. I'm only going to integrate out the high energy states. So I'll have minus d plus delta d. And this is going to go from d minus delta d. So the basic idea is that I have some density of states here. This is energy E. This is my density of states. This is minus d. That's d. And instead of doing the integral over all energies, what I'm going to do is just integrate over a tiny window here. This window and this window. And call this width delta d. And what we're going to say is that you integrate out the high energy mode. So that's sort of like a canonical transformation that we've just done when we went from the Hubbard model to the super exchange model. You did a canonical transformation, you got a different model, which was, we went from the Hubbard model to super exchange model. So here we're going to say we're going to do a canonical transformation where we get rid of the high energy modes, but we're going to come back to the same model. And the only difference would be that the new model has a smaller bandwidth. Okay, so it has a bandwidth which is twice of d minus delta d. So we're going to say that this expression here is actually the change in jk. So if I make a small change in bandwidth, delta d, then the change in jk is given by this. And in the RG, then you say that you write it as a differential equation because you're changing the bandwidth and you're changing coupling. And as you change why this is more than just perturbation theory is now you change the coupling by integrating this out, and then you do the whole thing again and again and again. But the next time you do it, you'll do it with a different coupling. So formally, that correction has been iterated. You're not just doing first order correction, you're iterating it. Because the lower energy states include the high energy state to higher order, because that's they already account for the fact that the high energy states got renormalized. The low energy states got renormalized by integrating out or removing by canonical transformation the high energy states. So this way, if you write the change in bandwidth, delta D minus delta D, you write is D times e to the minus delta L. This defines the delta L. Then you'll get an equation, which is djk dl, and it turns out to be basically jk squared with some coefficient that you have to work out. So this is you get a differential equation which tells you how the Kondo coupling flows as you change the bandwidth. And this is a very simple equation to integrate. So this is jk, and this is 0. Basically, this just means jk keeps increasing forever and goes off to infinity. Now, you can't really conclude that it goes off to infinity because this is only true for small jk. There are corrections of order jk cubed, which are much harder to compute. So this first term was, I guess, is sometimes called the poor man scaling term. It was obtained by Yuval and Anderson. And then Wilson developed, more formalized the whole idea of the renormalization group with a very different motivation, and did a computer calculation where we got the whole function here, not just the first term of order j squared. And that whole function confirmed that this naive correct interpretation that jk just goes to infinity is correct. Okay, so I'm just summarizing, some basic facts. That was rather quick, but just to give you the flavor of what the RG is and what its implications are for the Kondo model. The bottom line implication is that jk flows to infinity. Okay, so if Jake, any questions? So if jk really flows to infinity, what's happening? Well, so let's go back to the original model. Suppose I have the lattice model here. I started out with very small jk, and what I learned from the RG is that jk flows to infinity. So this is coupled to the spin here, and this jk is going to infinity. So in particular, let's assume jk is much larger than the hopping matrix element between the sites. So there's some hopping matrix elements, and there's j. That's the only two energy scales in the problem. So what we were doing initially was we were minimizing the hopping energy. We were just filling the lowest energy states, and we had a Fermi level, and we were just starting from there, free electrons. But now, if jk is going to infinity, what we should do is make jk happy first. And what jk is going to want this electron to form a singlet with that electron. So this will just become, the usual spin singlet state, up, down, minus, down, up. So this is sometimes called Kondo screening. So basically, the impurity electron borrows one electron from the Fermi C, one and only one in this large jk limit, and those two of them form a singlet. And now, what about the other electrons? Well, the other electrons are forbidden to come onto this site, because if they came on that site, you would break apart the singlet, and you could certainly put it by Pauli's exclusion principle. If this the electron, the singlet was up, and so one of them refers to the electrons in the conduction band, the others on the d side. So the up electron, if the conduction band electron is up, you can add another electron on the conduction band, which is down. But then the up-down pair on the conduction band has spin 0, and so that cannot form a singlet with the impurity spin, and therefore you lose the energy jk. So basically, once these two have formed a singlet, this side is forbidden. And the way you can then write the effective Hamiltonian for the conduction electron, now it only has the conduction electrons involved. It's sum on k epsilon k, C dagger k alpha, C k alpha. But now you have a potential U0, which acts on the electron on the origin, C dagger 0 alpha, C 0 alpha, and U naught goes to infinity. So that's our low energy theory. The impurity spin is totally screened. It forms a singlet in the limit of JK goes to infinity. And the remaining electrons basically see a hard sphere at the origin. So basically they can't hop on that side. They have to go around. Let's imagine we are in 2 dimensions. This picture seems like the electron will be blocked from moving. Well, it's not. It can go around it because you're in 2 dimensions or 3 dimensions. And that's a perfectly solvable problem. I mean, it's just a scattering problem. Suppose I have a square lattice with a missing site. Well, I could give that as a homework problem to figure out what's the scattering T matrix and the phase shifts and so on for that problem. And it's in fact, there's some finite phase shift and finite scattering amplitude that you can compute. Just a hard sphere scattering potential at the origin for the conduction electron. So basically, in the end, you find that as JK goes to infinity, the picture is extremely simple. There is no moment left over. It's completely gone and is bound into a singlet. Yes, question, Muching.
Hi, Subir. I have a question regarding this effective Hamiltonian. It seems that when we have this infinity U on the 0 side, does this break the translational symmetry? Could we still write the first term as kind of in momentum space?
Well, yeah, the model itself breaks translational symmetry, so you're not going to restore translational symmetry. I mean, you could have, in a sense, if the impurity site scattering potential went to 0, then you would restore scattering translational symmetry. But here, once that electron sitting here has formed a singlet with this site, then no other electrons are allowed to come to that site. So you can account for that by just a local scattering potential, which acts on all other electrons. Yeah, I mean, so that's the theory, just free electrons, except that they're not translationally invariant. It's a little more difficult to solve, but it's not that hard. In fact, this is just, if you think about it, just a variant of the resonant level model that we started with. It's another version of it, and you can solve it in exactly the same way, just by summing Green's functions with repeated interactions from the origin, just from the, and basically you just open your theory, your textbook on scattering theory, or you draw some Feynman diagrams and you can sum them all up and get the answer.
I see. Yeah, but I have another question regarding the first term, the conduction band electrons, because we can write them in quantum number of momentum k, that this already assumes translational invariance.
Yes, I mean, this term is translation invariant, but this term is not. Full Hamiltonian is not translation invariant. Right. So this is the bare, the bulk. I mean, the point is that it's just one impurity. So one impurity is not going to change the conduction electron far away. I mean, you have an infinite lattice with one impurity. So this is the infinite part, and it doesn't change. The only changes are near the impurity, and that's the change here.
I see. So it's like an approximation.
No, this is in fact in the limit of low temperatures, or you have to do some RG. It's a little more complicated, but if you do the RG and JK goes to infinity, let me say it another way. I had the Kondo Hamiltonian. I wrote down this Hamiltonian. And if you just allowed me to work with this Hamiltonian and take JK goes to infinity. Suppose I tell you I have this Hamiltonian and JK is infinity, and I ask you to solve the problem. What would you do? Well, you would say, okay, JK is infinity, therefore these spins are going to form a singlet. Then once these spins form a singlet, it means that I can't add any more electrons on that site. So then in the limit JK goes to infinity, this effective Hamiltonian with U naught going to infinity is in fact exact. That is the effective Hamiltonian that describes my low energy subspace. in the limit jk goes to infinity.
I see. Yeah. Thank you very much.
Okay. All right. So that's the RG and the strong coupling limit, and it gives a very intuitive and appealing picture of what's going on. And one thing I forgot to do. I think I said that last time, and you can also see it from the RG. Yeah, okay, let me just repeat what I said last time, and you can read the notes for further discussion. That is, so you have this correction, 1 plus 2 jk d of 0 times log of 1 over temperature. You ask at what temperature does this correction becomes of order 1, and when you estimate the temperature, you get this estimate of the Kondo temperature. It's exponentially small in the bare Kondo coupling. Okay, and this particular expression for the Kondo temperature, you can also derive by integrating this equation at small l, but I think I'll skip that because that's really more proper for an RG course. Oh, I should say, I did mention this last time, this kind of equation of the coupling constant becoming strong as you go to lower and lower energy or lower temperature is exactly the same equation that you get for non-abelian gauge theories in 3+1 dimensions. So if you take the SU3 gauge theory that describes confinement, interaction between quarks, just pure gauge theory, it has a gauge coupling constant G, and the RG equations for the gauge coupling constant is exactly this equation with some coefficient here that's slightly different. And that tells you, if I just replace this by G, that as you go to lower and lower energy scales, the gauge force becomes stronger and stronger and stronger. And that's interpreted as the confinement phenomenon, that as very strong coupling, the gauge force is so strong that the quarks will be bound into color singlets, which are, of course, the proton and the neutron. And it's also stated as asymptotic freedom. Deriving this equation for QCD is what got the Nobel Prize for Gross, Polchak and Wilczek, Politzer and Wilczek. And it's asymptotic freedom in the other way. So suppose I reverse this and I look at very high energies. Well, at very high energies, it says the gauge coupling goes to 0. And then you just have essentially free gauge bosons with some log corrections. And that is, and those log corrections are seen in deep inelastic scattering at accelerators. And in our case, the complete analog of that log correction is this term here. So the upturn in the resistivity of the Kondo model that Kondo explained from this log term is the exact analog of the log term seen in deep inelastic scattering of hadrons, and that gave precise evidence of the correctness of QCD. And the connection, of course, the models are very different. The details are very, very different. But the connection is they're the same RG equation. Okay. But there's also, a sense in, you can think of this as here as JK goes to infinity, this is confinement. What's confined? Well, what's been confined is the moment on this side. So when JK is 0, if you look at very high temperatures, if you're at very high temperatures, then you can just ignore JK, and then you have a free moment here. And this means that if you measure the magnetic susceptibility, so this will, this is worth saying. So at T much greater than TK, if you measure what's called the impurity susceptibility, that's the response of the impurity to the magnetic field, this will equal the Curie susceptibility of a free spin. So that's something I imagine you remember you worked out in your undergraduate stat mech class. It's 1/4 temperature. And that, so that appears to diverge as temperature is going to 0. So if I plot chi as a function of temperature. So I'm looking at very high temperature, that you get a term that seems to be diverging. But of course, it doesn't diverge because this is a high temperature limit. So now you can ask what happens at T much smaller than, there's some Kondo temperature and T much smaller than TK. What's going to happen? Well, at T much smaller than TK, there's confinement. So, and the confinement here is that this free spin that you had, which is giving you this large susceptibility, is confined in a singlet with captured a conduction electron and form a singlet. And it's tightly bound. So this singlet is the analog of the proton, where there's no free colored charges left. So here now there's no free spin left. And so what would be the magnetic response of such a system? Well, there's everything is from the spin is just locked into a singlet, and then at least at at leading order as JK goes to infinity, you would say, well, it's just 0. But there is a small correction due to the fact that JK is not strictly infinite. So if you work it out, it's like 1 over JK or 1 over TK. And so that's actually what happens. If you look at the actual susceptibility, instead of diverging as Curie would predict, it saturates. And so this is the behavior at T much smaller than TK. Okay. This my beautiful curve got a kink. It's not supposed to have a kink. Okay, it looks something like this. Yeah. So this is for T much smaller than TK. Yeah, that's fine. And now chi is equal to 1 over, well, let's say 4 TK. So it goes from 1 over 4T, but when temperature becomes about a TK, which is the confinement scale, it just saturates and becomes 1 over 4 TK. And this you can view even as the precise definition of what TK is. It's not the usual definition, but this is one possible definition. And so this temperature scale here is TK. Okay, so now you understand confinement, at least in this very simple model. Well, it's a very interesting and rich model, but there it is. Any questions? Okay.
Hi, Subir. I'm a little confused. Could you elaborate a little bit, like, why do you use the term confinement here? Somehow it's not clear for me. For one spin, like what does
yeah,
this
well,
mean?
I'm just trying to make an analogy. If you think of Curie susceptibility as evidence for the existence of a free moment, unpaired spin, so that's free. So if the Curie susceptibility disappears, it means your spin has kind of been neutralized or confined. I mean, okay.
I see.
That's all. I mean, but there's no gauge forces here as such. So you're right. Strictly speaking, if I want to really talk about confinement, then I'm implying that there's some gauge fields, then this is not confining. But pretty soon, not today perhaps, but next lecture, we're going to introduce emergent gauge fields. And then you'll see the analogy will become much more precise. In fact, what we'll see is that if you want to make it more precise, this Kondo screened phase is not really a confining phase. It's actually a Higgs phase. But in some level, Higgs and confining phases are the same in gauge theories, you may know. Yeah, but we'll see that shortly.
Yeah.
Excuse me, Subir.
Yeah.
Sorry. Just wonder what's the correspondence scale for the Kondo problem in the correspondence of Yang-Mills or the theory that you say confinement. There is an energy scale, the energy gap that can be global or maybe.
Yeah. So there is. Yeah. So this is a gap. This is a gapless system, but nevertheless there is an energy scale, which is the Kondo temperature, which is the analog of lambda QCD. So Kondo temperature is just like lambda QCD. And you can even see that it depends, lambda QCD depends exponentially e to the -1 over the gauge coupling constant. And that's exactly the dependence you have here also.
Okay, but the problem for confinement in QCD, that was a problem even for zero temperature, a purely quantum mechanical problem. But here in Kondo problem, it maps to the finite temperature.
No, you can, I mean, temperature is just my substitute for energy. You can also do measurements as a function of frequency at zero temperature, whatever. I mean, deep inelastic scattering, you're putting in frequency, right? You're putting in energy. So you can actually put in energy by having a frequency dependent probe, and there'll be very similar crossovers. It's just I would like to think of temperature as, it's a much more convenient.
Okay, experimental probe. More easy
Yeah.
for experimental probe. Okay.
You have some experimental probe with some energy scale. It could be temperature, it could be frequency, it could be magnetic field, whatever. They will all have some scale which is of order the TK.
But that scale change to maybe zero temperature problem. There's still an energy scale related to the coupling JK. And
yes.
Okay.
There is.
But
I mean, you could take the T matrix, for example, at zero temperature, and you'll find the TK scale. I will actually get expressions for T for such things, precisely in the next chapter or this next section. All right, so all of that. So now what I'm going to do is, any other questions? Good questions. So that's, yeah, I mean, just everything I've said today, was the topic of huge amounts of discussion and debates and excitement for over 20, 25 years, 60s and 70s, early 80s. Okay, so I want to give another way to solve the Kondo problem, which, you might say, why do I need it? I have the RG, you have the perturbation theory, and there's also a Bethe-Ansatz solution that people found, which confirmed everything I've just said. So there was, the whole problem was just fully solved and understood. But actually, around the time I was in graduate school, there's a new method that came by, which got the same basic results in some approximate way, but did it very simply, and also it has this natural generalization to the Kondo lattice, which will be the next chapter. And for the Kondo lattice, all these other methods I mentioned are not that useful. So that's why I want to introduce this method and go through it in some detail. So the basic idea is you have this impurity spin, SD. I'm just going to imagine that there are actually electrons there, which I'll call F electrons. Okay, just for convenience, you could call them D anyway, but I want to distinguish these electrons from the original electrons in the Anderson model. So I'm going to call them F. And sometimes they're called spin-ons because they're associated with a spin. They're not real electrons in the sense that their occupation number cannot change. There has to be one electron, one fermion there all the time. It's either spin up or spin down. So there's a constraint. So in fact, that's why they're not. The sum over alpha, F dagger F alpha is equals to 1. So these are not electrons, they're fermions with a constraint. F dagger alpha, F alpha equals 1. So you have to do a theory of constrained fermions, where that's equivalent to working with the spin a half. It's a constrained fermion. So if there's some simple way of imposing this constraint, then you've made a lot of progress, because now you can use Wick's theorem. Once suppose you could impose this constraint in some nice way, and then you have the hope that since you're working with fermions rather than spins, Wick's theorem will be available to you. Okay, so the way you do this is most clear in the path integral language. And I imagine not all of you have seen path integrals before. I think Ryan is going to cover some of it yesterday. Is that right, Ryan? But
yes, I covered part of it yesterday. Yeah.
Okay, but I'm going to avoid it. To really do everything correctly to all orders in what's called the 1/n expansion, you really need path integrals. and to impose this constraint. But if I only want the n equals infinity theory, then I can do without mechanisms. And the idea simply is that instead of imposing this constraint exactly, we're just going to impose on the average. And that means that we're not going to actually impose this constraint. We're going to impose that the expectation value of this is equal to 1. So that's an approximation. And that approximation becomes exact in a certain limit. And that limit is where the number of spin components, right now we're talking about just 2 possible spins, up or down. Suppose there were n possible states for the spin. Then in that case, the symmetry goes from SU2 to SUN, if you know what that is. And in the limit as n goes to infinity, this imposing the constraint on the average becomes exact. But when we did BCS theory, we didn't bother. We did Hartree-Fock theory. We just started factorizing the 4 fermion interaction willy-nilly. And basically, that's exactly what we're going to do here. We're going to factorize all interactions and impose the constraints on the average. And if you really want to be a stickler for the details and understand the corrections to this, well, then there's the 1/n expansion. But if you just want the mean field theory, then this is fine. So basically, we're going to impose this constraint on the average and do a Hartree-Fock theory. And that gives us, in fact, almost all of the physics of the Kondo effect. It's amazing how well it works, and it's amazing it wasn't done before. Well, people were developing these fancy methods, but I think people just didn't think that something this simple would give you the all of the physics. Okay. So in this sense, this is very different from the gauge theories. If you take the gauge theory and take large n limit, then that leads to a very complicated problem of large n limit of matrix models, which eventually has connections to gravity and string theory and so on. But here, the large n limit is much simpler. But it has the physics I've just discussed. So that's the basic idea. So I go through here in the notes the path integral method, because eventually we're going to need it for the purposes of this discussion. Let's just skip that, and let me just do it using the Hartree-Fock type method. So here's our Hamiltonian. The full Hamiltonian is the conduction electrons, epsilon k c dagger k alpha c k alpha. And now I'm going to write the interaction, which is going to be jk, and it's sigma dot sigma, but using some identities, you can write it as sum on alpha c dagger, what is it, c dagger 0 alpha f alpha. Well, let me write it out the full way first, in case. Yeah, let me not. So it's jk over 4. It's c dagger 0 alpha sigma c 0 beta dotted into f dagger 0 alpha sigma f 0. I should call them gamma and delta, excuse me. And then I have this constraint, and I'm just going to impose this constraint by a Lagrange multiplier, which I call lambda bar times sum on alpha f dagger 0 alpha f 0 alpha minus 1. So there's my Hamiltonian. This the main approximation here is I've imposed this constraint that f dagger f is 1, just by imposing lambda bar is sort of like a chemical potential. And if I just demand that the energy is stationary with respect to lambda bar, the Feynman-Hellman theorem will tell me that the average value of this is 0, which tells me that the constraint is imposed on the average. Okay, so this is the Hamiltonian you're going to work with. And now you just apply canonical Hartree-Fock. So you just do Hartree-Fock. And you only factorize in the particle hole channel. So when you do Hartree-Fock, let me write it out. I'm just doing Hartree-Fock. And the large N limit tells you there's only one term that you keep. And so then H becomes, so basically the only term you have to keep track of is this one. So this, you're right, you do the factorization. You can take the, so let's just think about it. So if you're only going to factorize in the particle hole channel, you could factorize this with this, take the expectation value of C dagger C, but that's just completely on-site and gives you the density of spins on the on-site, and the density of spin on any site would be 0. So that's not terribly useful. So you only useful factorization is to factorize this C dagger with the F. You get this cross factorization. And for this to be spin rotation invariant, that means alpha must equal delta and beta must equal gamma. And there's some factors of 2 that you have to keep track of. So when the dust settles, what you get at the end is, I think you get a JK over 2 times factorization of C dagger F times F dagger C. I'm dropping all the indices because they're in the notes, plus the other term, plus F dagger C times C dagger F. And then you get the double counting correction, C dagger F times F dagger C. Okay. And now what you do, you give this object a name. This object we're going to call Q over JK. It's just a number, so you call it Q over JK, and you plug it back in. And then basically you're going to find self-consistency condition for Q, with that Q is JK times expectation value of C dagger F. Okay, so that's the basic result, and here's the result stated in the notes. Okay, so you get a mean field Hamiltonian. Here, mean field is represented by a bar. This is the mean field Hamiltonian. It has an F dagger C and a C dagger F. This is just the free conduction electron. Here's a constraint, and here's a Q squared term. The Q squared term was the product of these two terms right here, this term here. Okay, and then there's so there are 2 equations you have to solve. So there are 2 parameters here that you don't know, which is Q and lambda, Q bar and lambda bar. And these are determined by 2 equations. So Q bar is equal to JK over 2 times JK times C dagger F. Okay, there's some factors of 2 that are now corrected here. Here, this is for general N. So Q bar is JK times C dagger F. That's how we define Q bar. And F dagger F is 1. We write it in a peculiar way in the large N limit. Okay. So these are the 2 equations you have to solve for Q bar and lambda bar. And there's your Hamiltonian. It's just a free fermion Hamiltonian. Okay. So that's all we're doing now. It's almost exactly what we did for the BCS theory. For the BCS theory, you had a free fermion Bogoliubov Hamiltonian with a parameter delta, and there's a self-consistency condition. Here you have 2 parameters, Q bar and lambda bar, and so you have 2 self-consistency conditions. All right. So from this point, it's just algebra. So I'm going to, the algebra is all worked out, and I'll just leave it for you to follow in the notes. Let's just go ahead and solve this. Okay, first of all, what is this free fermion Hamiltonian? Well, this free fermion Hamiltonian we've already solved. That's how we started the chapter. It's exactly the resonant level model that we started this chapter with. There it is. So if you look at the resonant level model, where is it? Oh gosh. Yeah, this model. It's exactly this model. The only difference is that this hybridization W, which we're now calling Q, has to be determined self-consistently. But other than that, it's the same thing. And there's a constraint on the chemical potential, so which is the same as the value of lambda D. So it's the same model, except the values of W and epsilon D have to be determined self-consistently. So that's why we talked about this resonant level model. We worked out all its properties. And now we can quickly use those, just replace W by Q and epsilon D by lambda. That's all. And then you get the results that you want. You just have to determine those numbers. Okay, so I can, let me just, it's really algebra. And so for example, you may remember in the resonant level model, on the impurity side, the Green's function, imaginary part of the Green's function was a Lorentzian. So there was a lifetime for the resonant level, which I called gamma then. Now I call it gamma Q. And gamma previously was by Fermi's golden rule, pi times W squared times the density of states. Now it's gamma is pi times Q squared of the density of states. And then we also need this particular Green's function, which we also computed there, because we need it in the self-consistency condition. So when we have to solve for Q bar, I have to look at this equation, and I need the Green's function. And that Green's function in the resonant level model, is very easily determined because all the Feynman graphs are very simple. They're just these graphs. This is an F, and that's a C, and there's an F, and that's a C, an F and a C. These are all the graphs. And every time the one converts to the other, you get a factor of Q. So it's just a geometric series that you have to solve. So when you take this, these are the expressions that you get, GFC and GFF. GFF is a Lorentzian. The spectral density is a Lorentzian. GFC is just basically GFF times G0CC times Q bar. Okay, so you take these expressions and finally you try to solve the two equations, and basically the two equations become this equation here and this equation here. Okay, so fortunately the equation for lambda bar is very simple here. It's just lambda bar equals 0. The whole problem is particle hole symmetric, assuming a flat density of states and so on. So lambda bar is just 0. So you just have one equation left, and that's the equation for Q bar. So here's the equation for Q bar that we want to solve. So that's the new thing. So all the non-trivial stuff is in this equation. So what are the ingredients? This is just, of course, just some integrals over Fermi functions. This comes from the Lindhard response function that you know between the conduction band and the D level. And AF of omega is the Lorentzian right here. So but it depends on Q because the width of the Lorentzian depends on Q. So basically it's, if you think about it, this is like the Lindhard function between a conduction electron and a Lorentzian. So width, level of finite width, and this is just the conduction band with a constant density of states. And this whole thing depends on Q through the width of the Lorentzian here. Okay, I think I should stop there. So that's the equation that we have to solve to figure out what's Q. And then gamma. And what we'll find is basically this energy scale gamma, which is a lifetime of this effective resonant level on the Fermi level, is the Kondo temperature. So there, to answer your question, Juven, there's a 0 temperature quantity. This is the lifetime of this resonant level on the Kondo site. that is the Kondo temperature. Okay, so there's a very narrow width as far as the conduction electrons are concerned. The conduction electrons see this resonant level, they scatter off it. That has a very narrow width in energy. That width is the Kondo temperature. And to see that, you have to just solve this equation for Q and see what's the solution. Okay. So one obvious solution you can see from here is Q equals 0. You can just cancel Q here, cancel Q here, and that's a solution. It turns out that's never the right solution for the Kondo problem. And that's equivalent to the statement that there's never a free spin. The free spin is always screened by the conduction electrons. That's the basic Kondo effect. And to make sure there's never a solution with Q bar equals 0, it turns out that happens because this whole integral has a log divergence. There's the log, which is kind of similar to the BCS log. And that's pretty much also the same reason why no matter how weak an attractive interaction in BCS theory, there's always pairing. Here, there's a log divergence associated with the Kondo effect. And that means there's always Kondo screening, meaning Q bar is always non-zero and gamma Q is also non-zero. But to see the log divergence, I have to study this equation a little more carefully, which I'll leave for next time. But I urge you to read the notes to see how I got to this equation. And I'll start at that point on Monday. Any questions? And I'm going through all this trouble because I think hopefully on Monday I'll be able to do the lattice in one fell swoop, because this whole formalism is so easy to extend to the lattice. You just have to make one change. Basically, the F level becomes dispersionful rather than being dispersionless. There's no momentum label on the energy omega of the local F electron here. And that has many interesting physical consequences. Yes, Juven.
So usually the most interest, there's a Holy Grail problem for Yang-Mills or QCD is 4 dimensions. But the Kondo problem, usually people study 2 dimensions, so also other dimensions, 1+1 or other dimensions.
So this, the Kondo problem, okay, 1 is slightly different because the bulk is not of free fermions usually. But the Kondo problem I'm talking about here is for 2 and any dimension 2 and higher. So it's this theory works for any dimension other than d equals 1. Basically, this K can be has any dimensions at all. The only thing I'm using is that d of E, the density of states, is a finite value at the Fermi level at 0 energy, at the Fermi energy. That's the only feature I'm using. Other than that, it can be work in any dimension. This K can have any number of dimensions you want. Okay, Martin.
Yeah, so sorry, maybe a very naive question. So how, it seems that the self-consistency solution for lambda bar is 0, but in some sense, it looks like we kind of remove this Lagrange multiplier.
Well, there's this lambda bar. Once you're writing it in terms of free fermions, it's just telling you that of spin, that there's a particle hole symmetry that that site has exactly 1 electron at all times. And that the only way you can do that with using free electrons is by just having the chemical potential right at 0 energy. Or, another way to see it is that there's a Lorentzian density of states. The Lorentzian is centered by lambda. Now the integral under the Lorentzian is 1, but you have to have the F band exactly half filled because there are 2 possible spins, and therefore you want exactly 1 electron. So if you look at the density of states on the F sites, there's a function of omega. This is GFF. You know, it's some Lorentzian. And it's centered at lambda. Now, if lambda bar is exactly 0, then in this free electron approximation, you will occupy exactly half the states. These are the states that will be occupied. So the total number of electrons, since you have 2 spins and you're occupying exactly half the states, is 1. So that's why lambda bar is 0, because this Lorentzian is half filled exactly when it's centered at 0 energy. If you were at any other value, then the number of electrons wouldn't be 1, including both spins. Yeah, so it's true when you're computing the energy and everything else, it doesn't appear, but if you want out doing corrections at order 1/n beyond mean field, then the lambda will play a role. But it sort of essentially drops out in the mean field theory.
I see. Thank you.
Any other questions? Okay, so I will have a discussion session tomorrow morning. I know some people are coming, so please, 9 a.m. tomorrow morning, Saturday. And we'll start again on Monday. Hopefully, I want to finish the whole Kondo problem on Monday. And then we go on to disordered metals and more complex topics. Finally, I should say quite a few have given me your presentation topics. It may be that you've given me your topic and I haven't put it on the website. If you don't see your name on the website, please contact me. I still have a few more people who haven't contacted me at all. And let's try to get that settled in the next few days. Thanks.